Okay. Hello, everyone. Can you all hear me online?
Yes.
Maybe I'm not hearing you. Give me 1 second. Yeah, I'm supposed to be hearing you. Can you write in the chat if you can hear me?
Yes, we can hear you.
Okay, good. Thank you. Okay. So let me share my screen. Okay. Then presentation. Let's get rid of this here. Okay. So welcome back to the lecture. So I have some comments regarding yesterday's lecture. So something that might cause a bit of confusion, I think might have caused a bit of confusion, is the thing about the frames, where they are located and we're moving on frames. But something that I forgot to mention is that actually velocities, both angular and linear velocities, are free vectors. So they are not bounded to a position, and that's exactly what I'm explaining here. So you're not confined to a point in space. So like position vectors that you need to define the specific point where the vector is passing through. That's not the case with velocity vectors. And we only care about their magnitude and their direction. So basically their orientation. And the other thing that might have caused a bit of confusion yesterday is that in the definition of the geometric Jacobian, I didn't put a left subindex. But it is actually important for me to mention that the axis ZI, the axis of motion, needs to be referred in the world frame. So in this expression, I'm adding the left subindex to the Z. So this set, the one that it's here. Let me just get my stylus. Okay. Thank you. So in here, I'm adding this left subindex to the ZI. Just it's important because then it would be very easy to get the Jacobian if every vector would be 0, 0, 1. So I actually want to do another exercise, like a bit more complex, with 3 joints and a prismatic one, just for you to get a feeling on how to get it and how to obtain the geometric Jacobian. So I prepared a new exercise. Now I'm not going to write the direct kinematics, but these were already derived in previous lectures. So here in this slide, we're going to work with this RPR robot that was Professor Focky already derived the direct kinematics. In this slide, I'm showing what we call the local homogeneous transformations, which are basically from one joint to the other. So they're not referred to all from 0. So it's just that from 0 to 1, from 1 to 2, from 2 to 3, and so on and so forth. And here I'm adding also the homogeneous transformation to the end effector, although it's a rigid transform. It's important to have it when you're computing the Jacobian. And then when we go to the global homogeneous transformation matrices, these were also already derived, and they were also in the slides. But which was the one that was not derived was the one to the end effector. We only had the local one. So in the bottom, I just performed the matrix multiplication, and you see the matrix below. I used the compact notation using the trigonometric identities, so that's why it looks smaller. But it's basically just performing the multiplications with the local transform from 3 to the end effector and all the previous transformation matrices. So we already have the direct kinematics of this robot, but actually what's going to be useful, it's going to be this vectors. So for example, we have the vector of position from 0 to 1, because remember that we have this difference between the end effector and the position of the current joint position frame, of the current position of the joint frame. So we have 0p1, this one represents 0p2, and this is 0p3, and the final one is 0 to the end effector. So here's 0, it's the world frame. It's the fixed frame. So once we have this, okay, let me go to the next slide. If you the only thing different from what we already did here is that I derived the last homogeneous transformation matrix. The rest it's all the same as from previous exercises. That's why I went a bit fast on this. But now let's talk about the Jacobian itself. So remember that the Jacobian is made out of the columns. The number of columns depends on the number of degrees of freedom that we have. So in this case, we have 3 degrees of freedom, which is those are the 3 joints that we have. The first one, it's a revolute joint, and the expression of the Jacobian for a revolute joint, it's basically this one. So you have the cross product of the axis of rotation of the joint cross the difference of the position vector to the end effector minus the position vector to the joint frame that we are looking at, which in this case it's 1. Then the second joint, it's a prismatic joint. It's this one here, the one in blue. Well, it's basically the whole rod of the actuator is going through that hollow cylinder. So that's the prismatic joint that we care about. And then the expression for the Jacobian column related to a prismatic joint, it's just basically the axis of motion of the like the linear part is the axis of motion of the joint axis, and then in the bottom the rotational part is basically 0. And then the third joint, it's a revolute joint. So again, we have a similar thing that in the to the first column, which is basically the cross product of the axis of rotation of the joint cross the position vector to the end effector minus the position vector to the joint frame. Okay, so then we have the Jacobian matrix here. So remember that set in all cases it's with respect to the world frame. In this case, it's called frame 0. So it's always referred to the world reference frame. So now we're gonna go through, because in the previous case, in the previous exercise, if you remember, both of the set axes were 0, 0, 1 because it was set pointing outside of the slide. But now it's a bit more complex because we have a prismatic joint, and then we have to do our rotation along that specific axis. I will go step by step. So the first one, it's kind of easy because it's a rotational joint, and the axis of rotation of the joint actually coincides with the origin. So this is very simple. It's as in the previous case. So basically here I'm showing first that we're expressing the axis of rotation of the joint, which is set 1 with respect to frame 1. But this, in this specific case, this is actually the same as in the world frame. So in this case, it's a very simple 0, 0, 1 vector. Now let's look at the second one, which is now located at this point in the robot. And here it's a bit more complex because we see that set it's actually not pointing outside of the slide, but it's actually pointing in that direction, aligned with the link that it's that with its predecessor link. So actually, if we look at the set axis of joint 2, this is expressed with respect to 2. Of course, this is 0, 0, 1, but this is not useful for us. We need to express with respect to the world. So we actually need to do a transformation using a rotation matrix. So we need to pre-multiply the vector by the rotation matrix of to frame 2 with respect to the world. Sorry, to the world frame. And now we're gonna look at how to get this rotation matrix. So I saw that I heard that somebody unmuted himself. Did I hear correctly? Him or herself? Okay. Then no. So let's get the computation of the rotation matrix here. So let's look at the at the first rotation. So actually, the first rotation that we have, it's a rotation due to the first joint variable, which is Q1. And if we look at the drawing, I drew it pretty small, but here we have theta 1 here. And we see that this axis of rotation, let me remove this from here. Okay. It's actually rotating in the at the same rate. Let's say the same, it's doing the same rotation as Q1, right? So actually the first rotation, we need to get the rotation from frame 0 to frame 1, because we're rotating that, and then we need to get the rotation from frame 1 to frame 2, okay? So the rotation from frame 1 to frame 2 is basically a rotation around the z-axis, rotating Q1 or theta 1 degrees. So this is just basically this, the basic rotation around the z-axis. And then for the rotation, for the rotation to the second frame, actually what I'm drawing here, it's a 90 degrees rotation about the axis x1. And here I'm drawing a more detailed drawing about, let's say, this part over here. But now, just to make it easier to see, here we have a rotation that is already more than 90 degrees rotated in the positive direction, which is counterclockwise. Here, what I'm drawing is, I'm actually drawing it at 0 degrees, so that it's easier to see the changes of orientations of the frame. So here we see that the frame 1, the one in red, it's orientated with the Z1 pointing outside of the slide. Whereas the purple frame, which is the frame of joint 2, Z is pointing downwards. So we need to actually rotate this frame Z to match the frame in Z2. Remember that we don't care about roto translations here. We just care about the rotation themselves. So we can actually just put the two frames on top of each other. And then the only thing that we need to do is find the rotation that makes the Z-axis match with each other. So well, how should we rotate the axis?
90 degrees around the x1.
Yes. So that's basically the thing, and it's a constant rotation, so that corresponds to this matrix, right? It's just a matrix of zeros. Sorry, 1 0 0 0 0 minus 1 0 1 0. Okay, and the result of the multiplication, if we substitute this rotation matrix, we get this vector. And an easy way to see, there are two ways that we can verify that our computation was correct. The first thing is that every set vector needs to be a unit vector. So if you make a mistake in the computation, it might be that the thing that comes out of Z is not a unit vector. So if it is not a unit vector, there's something that's wrong. The second way that we can compute, that we can check if our computation is correct, we can assign values to the angles. So for example, here, if we assign the value of 0 to theta 1, we actually see that if our joint is, it's basically this case, right? So in this case, our vector, the sine of 0 is, sine of 0 is 0. And cosine of 0 is 1, then we have the minus, so we have a minus 1 here. And this coincides with what we're seeing here, which is Z pointing downwards. So if you are in doubt whether your computation was correct, you can always substitute values of the angles, and then you need to see that it coincides with that specific condition that you're assigning. And then we have the 0 here. Okay, so let's move on to Z3. Again, we need to find the transformation matrix of from frame 3, the rotation matrix from frame 3 to the world frame. And actually, we can just do the composition of rotation matrices. So we have rotation matrix, the one that we already computed, and multiplied by just the rotation from 2 to 3. So we already have this from the previous exercise. And now what we need to find, it's a rotation of minus 90 about the x2 axis. And let me explain this in the same way as I did before. Now what I'm doing is, instead of having link that connects to the end effector as it is in the first drawing, I am rotating it as well to have a zero joint angle here. So what you see here is basically that X3, it's aligned with Z2, and Z3 now it's pointing outside of the slide, and Z2 it's pointing to the right. So we need, as it says in the slide, we need to actually return this minus 90 degrees around the X2 axis. And so we get this constant, so this is just showing a bit more detail, is basically the same thing as on top. And then we just, because it's a negative rotation around of minus 90, then we see that these two coefficients in the matrix are inverted. So in the end, if you do these multiplications, what we're going to find is that we actually return back the 0, 0, 1 because the x-axis is pointing on the other in this direction. So this was another thing that we could have done was basically just see that the axis is pointing outwards of the slide, and then we could just said, okay, this is 0, 0, 1. It's easy, but it's good to just do the method in case you have a more complex geometry, because let's say if you had a rotation around this frame, then it would not match this set 2. So it's good just to do the computation one by one. Okay, so we now have the Z axis, and now we already have the things that are circled in green, but we still need this differences here. But as I showed you before, we already have these elements here from the homogeneous transformation matrices, the global homogeneous transformation matrices. So it's basically just performing the differences between the vectors. So here I'm just showing what we already have from 0t to the end effector, and then this is just what we have from 0t1. Remember that the first one is just a pure rotation, so we just have 0, 0, 0. And basically we end up with this vector, which is 0pe. Then the second one, I'm just performing again the difference between the 0pe minus the one that you find in the homogeneous transformation matrix, which is this one, and you end up with this. Okay. So now let's go and get the cross products of the so the top part of the linear contribution of the Jacobian vector of I. So I'm just showing here that Z1 and Z3 both are pointing outside of the slide, so they are 0, 0, 1, just to keep in mind. And also here, what I'm showing is that we can actually represent the cross product with the skew symmetric matrix, as we discussed yesterday in the lecture about rotation matrices. So just as a reminder, this operator here, which is equivalent to what I showed you to be this one, it's this, and then this is equivalent to take the cross product. So in the end, if we perform these multiplications replacing the skew symmetric matrix operator, then we get this. So remember, this is 0, 0, 1. So this is the Z component, the negative Z component. So you get a -1 here, and you get a 1, and the rest of the matrix is zeros. So you get this matrix multiplication, which in the end turns out to be this. And then here I'm just doing the same for Z3. Again, remember that Z3, it's 0, 0, 1, so it's the same matrix as in the previous case, and you end up with this vector. So in the end, our Jacobian, it's this. I'm just substituting what we already computed. So are there any questions regarding this? Okay. So let's move on with just to finish this part of the lecture. So let's compare the relationship between the geometric Jacobian and the analytical Jacobian. So here I'm showing you the geometric Jacobian of the 2R robot, the previous example that I showed. And actually we see that the only elements that the only rows that have interesting elements are the first two and the bottom one. Remember that our two row, but it's something like this, right? And this kind of makes sense because the only task space variables that we can modify are x, and y, because you don't have a rotation or a translation around the z-axis. So that's why this row is 0. And then here you cannot rotate around the x or y axis because we don't have any joint that does that. So that's why in the bottom you only have once. And also what's interesting to see is related to the comment that I told you that that was in a blue square that says that we can only modify n task variables. So this means that we only can change two of the task variables, which are in our case x. In the task variables in this case are x, y, and phi. But we only have influence over these two, right? Because we can only change q1 and q2. This we cannot change. This one, it's a function of the other two. So this makes sense with respect to what we had. Now let's look at the analytical Jacobian that we derived before, which was based on the partial derivative of the direct kinematics function to the task space. And we see that actually the analytical Jacobian, it's basically made of the rows that have significant values of the geometric Jacobian. And this is I'm just highlighting this in the same colors. So this is what I explained. So the rows corresponding to the task space coordinate of the that are needed to describe the position and orientation of the 2R, those are the same as the unnecessary as the ones that are in the task space, whereas the unnecessary the unnecessary variables, as I explained, are just made of zeros. Okay, sorry. So this is just to see what relation exists between each other. So this is, you're going to find the coincidence between the geometric Jacobian and the analytical Jacobian based on the task variables that you can actually change. So again, let's see about, let's keep on comparing the geometric Jacobian and the analytical Jacobian. And remember that we had this expression that relates the angular velocity to the rate of change, in our case of the Euler angles, which is basically this matrix. This was explained in lecture 0.3 and slide 17. And basically we can represent this by a transformation matrix that it's only dependent on the angle of, I think we did roll and pitch. And so this is because the thing I'm doubting, because sometimes some people define roll, pitch, yaw, and some other define yaw, pitch, roll. So in this case, I think we did roll and pitch, roll, pitch, yaw. So the first two are roll and pitch, and it only depends on those two angles. And if we look at the expression of the Cartesian, so the Cartesian workspace velocities, which are these ones, which is the linear velocity and the angular velocity, we can actually get a transformation to the task space velocities. So in the case of the linear velocity, those are the same, right? So we have an identity matrix that just basically does nothing to the linear velocities, whereas in the case of the angular velocities, we have the transformation matrix that is on top multiplied by the change of rate of the Euler angles, and then in the end we get this this matrix, right? So if we look at this expression, this is basically the geometric Jacobian times the joint space variables. This is the transformation matrix that we computed above. Well, we call this TA, sorry, which is just a transformation matrix that maps from the geometric Jacobian to the analytical Jacobian, which is what I'm showing here, basically. So
The other way around.
sorry, you map the analytical Jacobian to the geometric Jacobian. Sorry. And this is made out of this matrix, which is easy to compute from this relationship between the angular velocity and the change of rate of the Euler angles. So just to summarize what we've seen in this lecture, we want to find the velocity, the linear and angular velocity of the end effector in the Cartesian space. We use the geometric Jacobian, which is made of both the linear contribution of the geometric Jacobian and the angular contribution to the velocity of the geometric Jacobian. Let me get rid of this. And these two, so JPI, it's a three-dimensional vector. JOI, it's another three-dimensional vector, and each of the rows of the Jacobian, it's a six-dimensional vector. And this is the expression that we use to compute the columns of the geometric Jacobian if the joint is prismatic or if the joint is revolute. Remember that set, it's with respect to the world. Here.
Sorry, the columns are 60 vectors, right?
Yes, the columns.
It's okay, it's okay. You said row, but
okay. So the columns. I meant the columns. If I said row. Okay. Then in the case of the analytical Jacobian, we want to find a mapping from the joint space, but now to the task space made out of the chosen variables of interest in the task space. And what we're going to use for that is the analytical Jacobian. And this analytical Jacobian is obtained through this deriving directly the direct kinematics function, which is, this is a mistake, actually. I didn't correct this here. In the previous slide, this is correct. This is n, actually. So n, it's the number of joint space variables, and m, it's the number of task space variables. So this is the expression that we use to compute the analytical Jacobian, although you can obtain it if you have the expression of the direct kinematics from your geometric intuition, but this is more systematic. And then we can transform between the analytical Jacobian and the geometric Jacobian using this expression, which in terms here on the left side, we have the relation between the velocity, the joint space velocities times the geometric Jacobian. Here we have what we define of our transformation matrix A. And then here we have our the multiplication between the analytical Jacobian and the joint space variables. So these are related so the geometric Jacobian is related to the analytical Jacobian through this transformation matrix. So you can move from one to the other using this TA matrix. And these are just the references that I used to build on this lecture. Are there any questions regarding what we saw or what we saw yesterday? Okay, if there are no questions, then I give the floor to Professor Focchi.
Can you open, is it connected
to the internet? Should be, yes. Let's see.
You need to open numerical kinematics, no writing. Numerical, no writing.
This one?
Yeah.
Okay. Just check if all the slides are fine.
Okay.
Can I look at this?
Okay. Let's move on with the next topic, that is employing straight away what we just defined, the Jacobians. Okay, and you remember we we computed previously inverse kinematics in an analytic way, and now we can see how numerical methods for computing inverse kinematics can be implemented using exactly the tool that Octavio just presented. So we remember inverse kinematics computes the joint variables relative to that correspond to certain end effector position or task variables. And at the velocity level, we should say, so inverse kinematics can be computed either at the position level, what we saw now, but also at the velocity level. And at the velocity level, we just invert the Jacobian. So we compute the joint velocity inverting the Jacobian times the derivative of task variables or the end effector or angular linear velocity or whatever we have. So the only problem is that we should be taking care that the inverse of the Jacobian exists. Otherwise, we will see some tricks to address this situation. But at the position level, there are some situations that we briefly introduced yesterday for which numerical approaches are mandatory. And this is the case of redundant robots, because you remember we have infinite solutions. And the other case is whenever we are not good enough to find a closed form solution, or this one does not exist, or is too hard to be found, or we're just lazy and we want to don't think about that and use this systematic approach. As inputs, inverse kinematics, numerical inverse kinematics, we need only the direct kinematics and the Jacobian. So these two things are the ingredients. And we can think about solving inverse kinematics, writing as an optimization problem and finding the solution of this optimization problem. And let's use this trick where, for example, we want to, sorry. This is the output we want to get. And we want to solve an optimization problem where we minimize a function. And what does this function, how does the function looks like? We want to build a function that is like this. And this function is always positive because we have a squared norm if you are not in the solution. And if we are in the solution of the inverse kinematics, which means we have a joint variable for which we achieve the desired end effector, then this cost goes to 0. So we can put 1/2, doesn't change anything here. We can define this as the tracking error at the end effector between what we corresponds to the forward kinematics of our guess of the joint variable and the desired end effector position that we want to achieve. So we try to solve an optimization problem that with some iterations finds out a sequence of joint configuration that whenever the optimum is reached, will correspond to the desired end effector position that we want to achieve. So this is like a cost function, and this, remember, this cost, it depends on the forward kinematics, which means depends on the joint variable itself. So our input is the end effector position then this is just an example, could be also the orientation in there, and the output it's the solution of this optimization problem, which is the correspondent joint configuration. Now, how does this optimization problem is it a linear problem? Is it a non-linear problem? A quadratic problem? Remember, the decision variable is Q. Is non-linear. Why? Very good. Yes. So the problem is non-linear because PDQ is non-linear, because we have sine and cosines that are non-linear function, and certainly they are not convex. So what is the problem with non-linear optimization problem? Did you ever heard about that? What is the main issue? Yeah, so they can have multiple minimum of this function. So nonlinear problem. Non-convex. And we have many local minima. Now, how would you solve this? Sorry, this was there. Yeah. How would you solve this nonlinear problem? We need to find a way to understand what is the minimum. And to compute the minimum, we need to compute the gradient of this cost function. But so let's see, the cost function is Q. We set to Q, and we want to see if it is a minimum or a maximum. We don't care. We have this necessary condition that the gradient should be 0. So in essence, this is a nonlinear system of equations that we need to solve to find that the point is either a minimum or a maximum. We don't have any guarantee, because this cost function could be like this. So it could have a minimum and a maximum. So the point where we start the optimization, we will see, will determine if we converge to a minimum or a maximum. But let's recall something about the calculus, that is the method of the tangent. This is the method that, remember, to find the root of a nonlinear function, you could have this procedure, and you start from, in essence, from a point, a guess, you evaluate the function, you compute the derivative, you find the zero of the derivative, and then you update again, you repeat the procedure until you don't converge to the real zero. So you take linear approximations of the nonlinear function, find the zero of this linear approximation, and iterate till you get to the zero of the nonlinear function. And this works good if the function is smooth enough, if it is not bouncy, if it's not really like this. And what we want to use to solve our nonlinear optimization problem is a generalization of this method of the tangent, which is for scalar functions, to the multidimensional case. So if we think about the Gauss-Newton approach, we start with a guess Q bar, we compute a linear approximation of the problem and solve it to find a new guess. And then we iterate till the solution converges, the solution of these linear approximations converge to the nonlinear system. And we see here an example with 3 iterations. So in this case, our nonlinear function is the error function. And it has this very nonlinear behavior. And we start at Q0 here. We go to evaluate the value of the error here. We take a linear approximation of this nonlinear function, and we find a zero, a new configuration of joints. So think about these are all vectors of dimension n. Then this new configuration, intermediate, we evaluate again the linear approximation to this function. We find a zero, and then we update this joint configuration, and we evaluate another linear approximation till the error of till the nonlinear function crosses the zero. So we have the optimum. And note that if we start from another guess, for example, from here, we could converge to another solution. For example, this one. Is it clear? Okay, so now let's find an approximation. So we want to do point 2. That is to find an approximation of this error function that is linear. So the approximation, we use Taylor approximation. We expand to the first order, and we are sure that we are linear. So we evaluate the function at the starting point, our initial guess, plus we take the partial derivative of the error function with respect to the variable, and we multiply, we evaluate this partial derivative at the starting point, and we multiply by delta Q, the increment. Remember this? Then how the partial derivative looks like, E is P minus P desired. So the partial derivative of P of Q will be the derivative of P in the factor with respect to Q minus the derivative of P desired with respect to Q. Now this is constant, let's say, is our input, and therefore we have this, that is the Jacobian. And remember, we need to evaluate at Q bar. So we have this expression, Jacobian, times delta Q. Then we solve this. So we want to find the we want to solve this linearized problem that is in the variable delta Q, because now we no longer have the non-linearities because we evaluated our Jacobian. So we have a matrix of number. So everything is linear in delta Q here. Therefore, we can write an optimization problem again that it's finding the value of delta Q that minimize what? This approximate error function. Now we call, to simplify the notation, this E bar plus JQ bar, which we call J bar delta Q. And if we to solve this, we can first express the Q norm, the Euclidean norm, explicitly. So we write this. I said I use the simplified notation. Transpose. You remember the norm can be expressed this way. And this is what? Sorry, doesn't change anything, but let's put 1/2 on top of that. And this becomes delta Q transpose J transpose J bar delta Q plus, we have the double product. That's why we put the 1/2. And the double product will become a 2, but we have 1/2, so we have this divided by 2, and we have 1. And the double product is like this. Plus, we have the these two. So we have the constant of the error E. So if we look here, we have a quadratic term. In delta Q, we have a linear term and a constant that doesn't depend on delta Q. Constant means that it's independent of delta Q. And what is missing here? 1/2. Okay. Now we can call this the Hessian. So because our cost is quadratic, we have a quadratic program to solve. And a quadratic program is, this matrix is called Hessian, and this matrix is called gradient G transpose. Now, because it's a quadratic program, is convex. So let's think about a multidimensional function with only a minimum. So we know that if we find a point where the gradient is 0, we are sure it is the minimum. Very nice, no problems. Because if it's not 0, it means that the gradient is the direction in the n-dimensional space where you have an increase of the function. It means that there is if it's non-zero, there is a point in which the gradient is non-zero, and so it's not the minimum, while here the gradient is 0. Now, so remember these costs, how does it look like? So if you do the partial derivative with respect to delta Q of a constant, what do we get? 0, okay. Then let's write it here. The value of delta Q that minimizes the linear approximation is the one that set this to 0, where the partial derivative is for the quadratic term. You think about what you do for a parabola, no? That you get the derivative is 2x. So the quadratic term has 1/2. That's why we put 1/2. We have the 2, and we have so if you have something like this, you will have something like this, and this will become the Hessian, and the x will become the delta Q. So this will be away, and this will remain the linear term, and the derivative of a linear term is the coefficient of the linear part, which was delta Q. But there is an issue here. Since the cost is a scalar, doesn't matter if we take the transpose of this, and because of the we want to end up with a column vector, in essence, we take the transpose of this. So doing the transpose of this is still a scalar, so we can do like this. The mistake. So sorry, how was before? Let me check. So before was E transpose J, and we get J transpose. So yeah, forget about this. We get the column vector this way, and we set it to 0. So we can find delta Q, the optimum, like minus J transpose E, and the inverse of this function that is the Hessian. Okay, so it's something like Hessian minus 1 times the gradient. And what is the problem with this computation? Do you see an issue?
The Hessian can be not invertible.
Yeah. Yeah, exactly. The Hessian can be not invertible. So there's a mess here. Because the matrix, if the matrix, let's say, is, for example, 6 times n, because you have n degrees of freedom, we have a redundant robot. In our case, we will see that we will define later what a redundant robot is. And then in the case of a matrix J transpose J, it's a matrix n times n. But the rank of this matrix, its maximum rank is the rank of the Jacobian matrix that has a maximum rank that is 6. So the maximum rank is 6 at most. This means that this is singular, and we need to find a way to deal with this. And the way people do is to do regularization. So they add to this session identity matrix multiplied by a small scalar that makes this matrix always invertible and definite positive. Positive definite. And this lambda should be bigger than 0, of course, and is around, could be selected around 10 to the minus 8. And this is called, we will see that, the damped pseudo inverse. The Jacobian. And then once we've computed the solution of this, you remember of this linear approximation, we want to update the guess. So we want to add to the previous guess this delta Q, and we find a new guess. And we compute again the error function. And if the error function it becomes lower than a tolerance, let's say epsilon, more clear, we stop. Otherwise, we do another iteration. We go back to point 2, we compute another linear approximation, we compute again the 0 of this linear approximation, and we iterate. Okay. Now, what is the problem with this approach? The problem is that you can get stuck in cycles. So we solved the invertibility problem by adding a regularization to the Hessian, but we could end up in situation, because we say that our function is nonlinear, so it's the red one. We start here, I don't know, we get here, then we go here, then it goes here, and we go back here and start. We never converge, so we will go always in this cycle. Or even worse, if we slightly go here a little bit backward, then we could even converge, diverge, start to diverge. So we never converge. This is because the function might initially decrease and then increase again. So what do you think could be a solution for this? This is our initial guess, or ETH guess, and this is delta Q. We should take something, a delta Q maybe smaller, like this, for example. This way, we know that the error function is decreasing locally if we don't move too far, right? And this is exactly the idea. Instead of we move along the Newton direction, but we take smaller steps until we get a decrease of the error. So if the step is like, I don't know, here, for example, if it's here, we have no decrease of the error because this point is here, but already in this point we have a decrease of the error, for example, because the error now is here. So the error decreases. So take smaller steps where delta Q is computed as before. And this is called step size. And is a number between, of course, 0 and 1. Okay. An observation is that if the error function was linear, then we would have a decrease of the error that if we take a step like alpha, like 0.5, we would have an error decrease by half. So the decrease of the error in the linear case is the amount of alpha, because if we set alpha to 1, we get the full decrease of the error to 0. But the nonlinear function is in general decreasing less. So in practice, we are happy with a fraction of the decrease that we would have in the linear case. So if the linear case decrease will be alpha of the error, then with a parameter gamma, we can ensure that we have enough decrease. But in general, if you want to care about this, you could say that you want at least a decrease. So you want that your nonlinear error at least decreases. But setting a value bigger than 0, it's just being more strict and ask for a better convergence. Because if you ask only bigger than 0, then the convergence can be very slow. Okay. Then how do we select the step size? This is an approach called line search. And we start with a value, I don't know, for example, 1. So we check the reduction of the error with alpha equal to 1. And for example, in this case, you can see that this is our initial guess with computer organization. We take a full step. So we go to here and we evaluate the error. And we see that the error, you should also always think about the norm of the error. So this length here is bigger than what we had before. So the error is bigger than before, not okay. We need to take a smaller step. So in general, I consider the reduction, and while the reduction is bigger than 0, I reduce the step. So I multiply the step of 1, for example, by a factor beta, for example, 0.5, and each time I reduce the step of half, and then I compute a new test configuration, and I check the error reduction for that configuration with respect to the previous iteration. And when the reduction is positive or bigger than something, the linear case, a factor of the error reduction in linear case, then I accept the configuration and I continue for the next iteration, and I continue for the next iteration. And so if you have a flowchart to describe this, you can summarize it here. So we start with an input and the factor position, an initial guess, and we compute the Newton step here for the linearized problem. We try to update the configuration. We check the error. If there is no reduction of the error, we reduce the step. We take another configuration to test. And if the result is reduced, then we check if the total error is close to 0 or close to a tolerance for the linear problem. And if it yes, we have the output. Otherwise, we solve another linearized problem at the new at the QI+1 configuration. Now, if we take, for example, this example with gamma equal to 0 and beta equal to 0.5, while the error is lower than equal because gamma is 0, then E test. We do what? A step reduction with beta 0.5. So we reduce by half and we compute a new Q test. Mamma mia. With where this was the Newton step, full Newton step. And if we manage to reduce the error with respect to the previous one, we accept the value of Q test for the next iteration. So here, for example, we have a ith iteration and we linearize, and the full Newton step with alpha to 1 goes to this point, and we check that the error is bigger than this one in terms of norm. So we reduce the step of 1/2 and we get this point. And at this point, the error is still bigger in terms of norm than this one. So we take again half, and then finally we find this point where the error is smaller than this one, and we stop the line search. And this is, we reduce the step of 1/4 to 1/4. Then an important, interesting fact is that you can see an equivalence of these schemes as a feedback scheme to the concept of a feedback, because you numerical method are taking the error and try to move the solution such that the error decreases, and the same thing as a control system does. So we have a input the factor position, and we have the error, and we see that the fact of updating the at each iteration this is the delta Q, that like a velocity, and we integrate to get like a configuration. So this is something like an integrator, and integrator ensures us that you remember the error, steady state error goes to 0. So when the system converge, we have a 0 error. So this is another way to say to see the same thing as an equivalence to a feedback scheme. Yeah, I almost finished. Just some implementation issues. Yeah. Let's finish our 2 slides. So the problem of this approach is that we need an initial guess, and we have one solution is generated for each guess. And you remember that we can have multiple solutions for the inverse kinematics. So depending where you choose the initial guess, you will converge to a different solution, and you need therefore different initialization to obtain all the solutions. And the stopping criteria can be, for example, a problem in case you have a orientation as well, together with the position, because you have a mixture. No, you take the norm and you are in essence comparing in the same error pear and apples, because one position are in meters and the orientation, for example, are in radians. So you might need to separate position and orientation variables. And you need also to check how close you are to the singularity to avoid the divergence of Newton method. We will see later what a singularity means in the next bunch of slides. And to check the singularity in general means to ensure a good numerical conditioning of a matrix J. And this means in a generic case, for example, where J is rectangular, to have a singular value, minimum singular value that is bigger than a certain threshold. And in the case of a square matrix, square J matrix, requiring that determinant is bigger than a certain threshold. So with this, we can check if we are close to the singularity, because close to singularity, this algorithm, they behave, they can have problems. And another point is that joint range limits. Remember that we have limits in our end effect in joint positions, and we need to check these limits only at the end. So only when the algorithm, the merge kinematics algorithm converges, because in the middle, we might, in the middle iterations, we might violate these limits. And one thing is that because we are talking about iteration, this algorithm can be slow. For example, think about we want to solve this inverse kinematics online. We want to track an effector trajectory that is changing each 10 milliseconds, and we want to solve the inverse kinematics to find the joint configuration to track, because we want to close the loop at the joint level. And if this takes time, we might have problem. So a trick to do is that a good choice for the initial position, for the initial configuration for the inverse kinematics algorithm, is to use the solution at the previous loop, so that the previous solution. And this way, the convergence will be very fast. Every 2 iterations, we will get a convergence, and we won't have any problem of convergence. Then this is an exercise that I let you do at home to the inverse kinematics for a planar 2R robot. We have as input, for example, the position of the end effector located at 1, 1, and we have the link that are 1 meter long, and we want to achieve a convergence of 10 to the minus 5, or at most 10 iterations. So we want to stop after 10 iteration if we didn't achieve this convergence. And if you do that, if you simulate that, you can do by exercise, you can find an error function that has this shape. And this is, we can plot it because we have a function that is a function of 2 variables. So we can plot in 3D as this is a scalar function of 2 variables. And if we take the contour curve of this, we see that there is a maximum here, there is another one here, and there are 2 minimum. And what do you think these 2 minimum are? Right, correct. The 2 regular solution of the inverse kinematics for a planar robot with 2 degrees of freedom rotational. And for example, if you start here as a guess, you might converge to this solution. If you start here, for example, you might converge to this other one. And this solution exactly are the elbow down, elbow up configuration. Because you see here, you have a positive, this is Q2, and this is Q1. You remember Q2 is this. In this case, Q2 is positive, while here Q2, this is 0, is negative. Okay, so we have the elbow up configuration, while here we have a elbow down solution. Now, what do you think? And in general, the separation line, it's represented by the singular configuration. So this configuration where the arm is completely stretched, which is what? For Q2 equal to 0. So this configuration. Now, what do you think the maximum corresponds to? So the farthest value from our design and effector. Remember, we have our designer and effector that is 1 to 1. Yeah, it's a singular configuration, but how would you locate the arm?
That one Like the end effector that the first.
So sorry, if we start from, I want to draw the the starting configuration at this point. And this is the one that has the highest error at the beginning. That's why it's in the maximum. So the highest error, if you think, is this configuration where you have a Q1 like this, and a Q2, a Q2 0, because this is the most far away from our requirement, and is will have the maximum error. And if you look at this point, indeed, you get a Q2 of 0, and you get a Q1 of, sorry, yeah, now drawing against, of 3, how much is that? 3 over 4 pi. So it's 270 degrees. Yeah, that's just a curiosity that you can do in this analysis. Everything comes back. So yeah, if you have any question. Otherwise, we can do the break now. Let's do 10-minute break. And we continue at 7:05. No, I just switch up the video here.
Oh, yeah. No, but also stop sharing because I want to shut down my settings.
Ah, okay.
Then we share again.
And I mute. Okay. Okay. Let's start again. This is the last chapter of the last topic of the bunch of lecture on kinematics. And in this lecture, we start to introduce, we don't do everything today, about the concept of redundancy and the singularities in robot manipulators. So first, we can see, I think it's important to see that redundancy and singularities are just two faces of the same coin. And the idea is that redundancy, when you have redundancy, you have more mobility, more degrees of freedom that you need, while in the case of singularity, you have less mobility than you need. And in particular, what do you mean more degrees of freedom that you need? You have, in case of a redundant manipulator, more degrees of freedom than the dimension of the task. So M is smaller than N, and we said before that we have infinite solution to the inverse kinematics problem, and the Jacobian matrix becomes rectangular. And we define a rectangular matrix for, in this case, is rectangular, lower rectangular, or fat. So with less rows than columns. Then what we do, what we can do with the redundant degrees of freedom, we can use, for example, these degrees of freedom to increase the dexterity of the robot, for example, for obstacle avoidance. If, for example, you have planar example of a planar robot of 4 degrees of freedom, and the task is to locate the end effector in the plane. So 2 position variable and 1 orientation, because we want to orient in the plane, we need only 1 orientation variable. And you have, for example, this obstacle here. You can find another configuration, flipping, for example, this joint up here, where you don't hit the obstacle. In this case, you have an infinite number of solutions to locate this point, for example. You can locate all around this circle. And this is a thing, for example, if you think about our human arm, it's like, if I want to keep the end effector position orientation constant, you have an infinite number of solutions of the joint that correspond to the same orientation and the same end effector position. And this is called self-motion. So self-motions are the internal motions in a joint space that do not affect the task variables. And these self-motions are present only in a redundant robot. Okay. Then we again remind that redundancy is a relative concept. It holds with respect to a given task. We can have different task dimensions. Position in the plane is 2-dimensional. Position in 3D space is 3-dimensional. Orientation in the plane is 1-dimensional. Pointing in 3D space, like with a laser pointer, it's only 2-dimensional. Position orientation in 3D space is 6-dimensional. So a planar robot, for example, 3 degrees of freedom is redundant for the task of positioning the end effector in the plane, but not for the task of positioning and orienting the end effector in the plane, because we have a task of 2 + 1, 3. Now, some example. For example, you can see a redundant robot has two cooperating manipulators. So this is the case of a Justin robot that is carrying a trailer, and you need to move. You see that you can have these internal motions to improve dexterity. Or you can have a 6 degrees of freedom robot with rotational joint mounted on a linear track, or having a manipulator on a mobile base, like a center or a manipulator on a wheel base. So on a robot that is moving on wheel and has a manipulator on top. Other example, for example, you can have a humanoid, and you can see here that a humanoid is a very redundant robot. And in addition, humanoid is underactuated, so has some degrees of freedom that are not actuated, like the one at the base. And you see that you can exploit redundancy to achieve a task and avoid an obstacle. And in this case, the task is to reach the ball. On the left, you are on the plane. The task here is to move the end effector on a bidimensional trajectory. We have only x, y, and we have a 6 degrees of freedom robot, and we can avoid the obstacle with these 6 degrees of freedom. And we have a redundancy of n minus m, so a redundancy of 4, because the m is bidimensional, and n is the number of degrees of freedom, that is 6. Okay. Now, we said that they can be useful, redundant robot can be useful to avoid collisions, but also to avoid the kinematic singularities. You remember, we don't want to get into close to them because they screw up our inverse kinematics. So we can reuse the redundant, we can use the redundant degrees of freedom to try to stay away from the singularities. We can increase the manipulability in specified directions. So let's say we want to be able to have a good mobility in a direction of motion we want to move in a pick and place machine. So we want to increase the manipulability, that is the relationship, the ability that the end effector has to move. So whenever we lose mobility, is that we have a big motion of the joints and we have a very small motion of the end effector. So in that case, we lose mobility. Or we can stay inside the joint ranges. So if one of the joints is reaching the joint limits, is about to reach the joint limits, the robot can reconfigure itself using the other joints to avoid hitting the limits. And we will see an example in the next slide. And in general, uniformly distribute joint velocities, or minimize energy consumption, or optimize the execution time. And the disadvantages are greater structural complexity in construction, because we have more degrees of freedom, more links, more transmissions, more motors, more actuators, higher costs, of course, and more complicated algorithm for motion control. We will see them in next lectures. And here is an example of our quadruped robot that needs to step down from a high pallet, 24 centimeter high. And we see here that was reaching the kinematic limit in the front legs here, and eventually it falls. While with this other approach, we exploit the motion of the other legs, of the stance legs, to aid the swing motion. So this prevents the redistribute the motion on the stance legs and avoid the hitting the limits on the on the swing leg, on the front legs that are swinging. And this is an example of exploiting this redundancy that is inherent in quadruped, in legged robots, let's say. Then we want to, because we want to analyze, it's useful to analyze redundancy and singularity to recall some concept about linear algebra related to the Jacobian matrix, because everything in essence can be described given the Jacobian matrix in a certain configuration. And we know that Jacobian matrix changes because with the configuration, because we have a dependency on the joint variables. And the Jacobian matrix in essence is a matrix of numbers. And as any matrix of numbers has some properties, and it has also some geometric spaces associated to it. And the first concept is the rank. We define it here formally. The rank of the matrix is the maximum number of rows and columns that are linearly independent. And in general, the rank, it's lower and equal from the minimum between the number of columns or the number of rows. So for example, if you have a 4 times 6 matrix, how much is the maximum rank that we can have? 4. If I have 6 times 6, and if I have 5 times 6, oh, sorry, a 6 times 5 matrix, it's 5. Good. And whenever the rank is equal to this minimum, we say that the matrix is full rank. So the maximum rank that can be achieved. In the case the number of columns and the number of rows are equal, then and J is full rank, then it means that the J matrix is non-singular and exists an inverse. And finally, we can also consider the rank as the dimension of the largest non-singular square submatrix of J that we call the minor, the minor of J. So all the square submatrix of J, even if J is rectangular, are the minor, and the largest one that is non-singular with determinant different than 0, then is the size of this matrix represent the rank. So the other concept, very important concept, is the range of a matrix that can be also defined from people as a column space or image space. So range space, column space, and image space are synonymous, and they are represented by the notation R of J, and this represents the subspace of the set that is represented by it's the subspace of all the linear combination of the columns of J. So think about if you have J that is a mapping from joint velocity and task velocities. So the task velocities are the range space is the set of task velocities that are living in the space, in the task space, for which we have a certain joint velocity associated. So if we think about joint velocity, a vector of joint velocities like Q1 dot, Q2 dot, and Q3 dot that we pack here, we see that the columns, each column is multiplied by this joint velocities, and we have a linear combination of the columns. So the end effector velocity is a linear combination of the columns of the Jacobian. And this represent the range space and represent the in essence the vector velocities that are realizable, so that we can realize with the motion of the joint. While the null space or kernel of the Jacobian, it's a subspace, is a vector space again, of all the vectors that are zeroed by the matrix J. So if you consider a vector in the joint space, and if this happens, so if you multiply this vector by the Jacobian matrix and you have 0, then it means it belongs to the null space. Yeah, an important point, I didn't say it, is that the dimension of the range space is equal to the rank of the matrix, while the dimension of the null space is equal to n, which is the dimension of the codomain of the joint space, minus the rank. And since it's a vector subspace, you can sum vector in the null space together, and you still will get a vector that lives again in the null space. Finally, the last space we are interested to, we will draw them afterwards. It's the row space. And this is the space spanned by the rows of J. Spanning means linear combination. So if you combine the rows of J, you obtain a vector that is part of the row space, or equivalently by the column of J transpose. So a property is that the row space of J is equal to the range space or the column space of J transpose. And another property, again, as in the case of a range space, the dimension of the row space is the rank. Then if we draw this you should remember it's very useful diagram that shows whatever we said. So the Jacobian matrix maps joint velocities that are living in a space that is n-dimensional, the joint space. And this joint space is partitioned into two. We see that they are orthogonal subspaces. Of course, we will have the null space only in the case of a redundant robot, we see. Otherwise, we have only the row space. And each vector that you can pick from this bag, from this set of joint velocity that represent our joint space, can have a component in the row space and a component in the null space. What happened if the component in the null space, if we apply the Jacobian, will go to 0, so we'll have no effect on the end effector, while the component of on the row space will go end up into the range space that has the same dimension of the row space. So this is directly going through here. And if we want to do the inverse mapping, so in here in the range space, we have the task velocities that live in the task space or RM. And the range space contains all the task velocity that are physically realizable. The inverse mapping is the pseudo inverse of the inverse of the Jacobian that we remember. We will see in case it's a rectangular matrix, doesn't exist. So we will compute the pseudo inverse that always exists. And the pseudo inverse is the inverse mapping and maps from the codomain, so from the task space, to the row space. So it does exactly the opposite that J matrix does. Okay. Then we have this important theorem that is the rank nullity theorem that basically tells that the dimension of the row space and of J and of the null space of J, it's equal to the dimension of the domain N, and the dimension of the row space, we said it is the rank. And this has some consequences. And the first one is that the row space that we said was equal to the range space of J inverse, J pseudo inverse, or even J transpose. We will see that the same. Both of them are true. The row space of J is orthogonal to the null space. So this is a consequence of this property. And we can see that if we sum these two spaces, we obtain back the whole joint space. Therefore, any element of the joint space can, in the velocity of the joint velocities in the joint space, can be written as a component in the row space plus a component in the null space, where the component in the row space belongs to the row space and the null component belongs to the null space. Then the same holds for the task space. The dimension of the range space of J is equal to the plus the dimension of the null space of J pseudo inverse is equal to the task space dimension, which is the dimension of our codomain. And the consequence is that the range space of J is orthogonal to the null space of J pseudo inverse. The whole task space is the sum of these two, and any element of the task space velocity can be written as a sum of null space component and range space component. Okay. So to finish, we do the drawing and we see that the effect of J is to filter out whatever is in the domain that belongs to the null space. So the part of the domain that is in the null space, it filters it and maps only whatever is in the row space, where into the range space. So the null space component is nullified by the action of J. And the physical meaning of these spaces that we will use in this course is that all these spaces, first we need to say that are locally defined, so depend on the current configuration of Q, and they will change with Q. And again, we summarize that the null space is a set of joint velocity that do not produce any end effector velocity. So this, for example, joint velocities are part of the null space. And this null space always exists when we have a redundant robot for the task. A robot that is redundant for the specific task, represented by the Jacobian. And the range space instead is the set of end effector velocities that can be realized varying some joint with some joint velocities in a given configuration. And if the rank, the matrix, the Jacobian matrix, is full rank, so in this case, for example, we are talking about a fat matrix, we have the rank equal to M, then it means that the end effector can be moved in any direction of the task space. We don't lose mobility in some directions. And if we are talking about a redundant robot, cancel this. If instead the matrix, Jacobian matrix is not full rank, so there are some, the rank is lower than the number of rows, it means that there are some directions that are corresponding to some rows in which the end effector cannot move. And we will see that this is the case of singularity. So again, using the concept of range space and null space, we can define both redundancy and singularities. Okay, we could stop here. We continue next lecture from this point. And if you have any question on this, we will use these spaces to analyze redundancy and singularity. And we will also, I also prepared some MATLAB examples to check the dimension of this space, to compute these spaces in the simple case of a planar 3 degrees of freedom robot, 3R robot. We will ask you what is your preference, because we are thinking about 2 ways of doing the exams. The exam could be a set of open question plus exercises plus some quiz questions, only written, or it could be a project where you need to, I don't tell you what, you will use the tools that you learn in the course. This project, we need to think if you could do offline at home, and then we do an oral session where we look at the project, plus we do some questions, theoretical questions on the concept of the course. So this will open up a poll in Doodle to ask you what is your preference, and then we decide what to do for the exam. Then I think we should do all the 3 exams the same. Okay. No, right?
We still haven't discussed.
We still haven't discussed, but
yeah,
I would
the
say
advantage is that it's easier, but then we need to see if the contents of the course have actually gone through, because usually when you do a group project, there's somebody that really understood well the concept, and then it's like it drags the other 2. So we need to see, but we haven't discussed it, but we are more inclined to make it individual.
okay. So see you next week with the new topic on dynamics and statics.
Thank you. Good evening.
Have a nice evening.